Hello everyone, welcome to the e-learning program of K.T.H.M. College Nasik. I am Dr.M.K.Deore from Department of Physics, K.T.H.M. College Nasik. Dear students, in this lecture we are going to discuss the sixth unit of the second chapter, Debye method. It is also known as the powder method. Now here we are going to see in details about the powder method. Students, in the previous lecture we have seen the two methods of the X-ray diffraction. One was the Lau method and second one was the rotating crystal method. Then why the powder method is useful as compared to the Lau method and the rotating crystal method. In case of the Lau method and the rotating crystal method, these two methods are useful only the single crystalline material, and in case of the rotating crystal method we need to rotate the crystalline material, that is the single crystal material. But we know that most of the crystalline substances naturally available in the form of the polycrystals, and if the powder specimen is used instead of the single crystal, then there is no need to rotate the specimen because there will always be some crystals at an orientation for which the diffraction is permitted. The main difficulty is the method of the preparation of the single crystal is quite difficult. So all these difficulties can be overcome by the powder method, and due to that nowadays powder methods are very important to study the crystalline structure of the different materials. The powder material consists of the huge number of tiny crystals and they are oriented in a different directions. If the crystalline substance is finely grounded and grounded into the powder, then millions of the tiny crystals in the powder are randomly oriented. Now see here in this diagram we can see that now there are the number of the crystals, they are oriented in a different directions. So when the monochromatic beam of the X-ray incident on such a set of the parallel planes, then there is the diffraction of the incident radiation, and we can record or we can study the crystalline structures from this diffraction pattern or from this diffracted beam of the X-ray. The Dutch American physicist the Peter Debye and the German physicist Paul Scherer proposed the powder method in 1916, and after then it was named the Debye method. The powder method is very useful for the determination of the value of the lattice parameters very accurately. We know that the lattice parameters are the magnitudes of the unit vectors A, B and C, which are useful to define the unit cell of the crystal. Now in first chapter we have studied about the crystal structure and also the lattice parameters also. The second application is that it is useful to determine the size of the unit cell and also the type of the lattice. So now in this way, in case of the powdered method, it needs the monochromatic beam of the X-ray, and in the powder material it consists of the huge number of the lattice planes, the set of the lattice planes which are oriented in a different direction. So they satisfy the Bragg's diffraction condition. 2d sin theta is equal to be the n lambda, and we get the diffracted beam of the X-ray from the powder crystalline material, and it is useful for the determination of the lattice parameter, the size of the unit cell, and the type of the unit cell. Here we are going to see the basic principle of the powder method. We know that the powder material consists of the millions of the tiny crystals, and these tiny crystals in the powder are oriented randomly. Now you can say that these crystalline planes are also as a diffraction planes, and all possible diffraction planes will be available for the Bragg's reflections. Such reflections will be the takes place from the many set of the parallel planes lying at the different angles to the incident X-ray beam. We know that in case of the powder material, now it consists of the number of the set of the parallel planes, and they are oriented in different directions. So for each set will give not only the first order reflection but also the higher order as well. For each set of the planes and for each order, when the incident X-ray beam incident on this set of the planes, then the reflected X-ray will form the cone, whose axis lies along the direction of the incident beam and whose semi-vertical angle is twice the glancing angle for the particular set of the planes. Now see here in this diagram we can see that now these are the number of the tiny crystals. They are oriented in different directions. Now when the beam of the incident X-ray incident on these planes which are oriented in different directions, when they reflected from the different set of the parallel planes, then they will form the cone. Now in this case here, this is the axis of the cone, and the direction of the axis of the cone is along the direction of the incident beam. Now see here, this is the vertex here, and now this is the semi-vertical axis. So from the different set of the planes, now there is the formation of the different cones for the different orders. So here the value of the semi-vertical angle is twice the glancing angle. Now here the theta 1 and theta 2 are the two glancing angles of the incident X-ray beam. Now in this figure we can see here, now see here, this is the photographic field. When the beam of the incident X-ray incident on the powder sample, then we can observe the diffraction also as well as the reflection also. Now when the beam of the incident X-ray incident on this powder method, then from this side we can see there is the formation of the cones, and these cones are due to the diffraction. But to this side, now here is also the formation of the cones, and these cones are due to the reflection of the cones here. When the beam will be incident on the sample, then due to the diffraction and due to the reflection of the X-rays, they interact with the photographic film and form the series of the concentric circular rings. Now then see here, now in this is, we can see that now here the width of the film is narrow, and due to that there is the formation of the, we can see the concentric rings here. Now this is the point where the incident beam enters, and this is the point where it exists here. So we can see at the incident point and at this exist point, now there are the formation of the different concentric rings here. So by recording the radii of these rings on the film, we can find the glancing angles, and with the help of the glancing angle we can determine the interplanar spacing of the crystalline substance. So now in case of the basic principle of the powdered method, now here the monochromatic beam of the X-ray is used, and when it get incident on the powder material, which consists of the set of the parallel planes which are oriented in a different directions, and due to that they satisfy the Bragg's diffraction condition 2d sin theta is equal to be the n lambda, and so the incident X-ray will be get diffracted here. Now in this figure we can see that this is the photographic film here. So here this is the incident X-ray beam. We can see the pattern developed on the photographic film, which is in the form of the concentric rings here. So now here to this side, now all these rings are formed due to the on this photographic film due to the formation of the cones, and it is due to the diffraction. Now then we are going to see in details about the experimental arrangement of the powder crystal method. Now see here, this is the schematic diagram of the powder method. Now it consists of the different parts. The first part is the X-ray tube, which generates the polychromatic radiations of the X-ray. Now here the filter, it is also known as the monochromator. Now here the collimator, it consists of the fine slits S1 and S2. Now here this is the cylindrical camera. It is also called the Debye camera. Now inside this Debye camera, the photographic film is mounted there, and the detector, the different types of the detectors are used to record the intensity of the diffracted beams. And now see here, we can see here this is the photographic film, and here how the pattern get developed on this photographic film. Now see is the specimen. Now here which the sample holder is there, and the sample is held by that the sample holder. Now here the X-ray tube acts as a source of the X-ray. Now it generates the polychromatic radiations, and if you want to make it monochromatic, then it should be passed through a filter. which is also known as the monochromator. After passing this polychromatic X-ray beam through the monochromator, we get the monochromatic beam of the X-ray, and it is collimated by the two fine slits S1 and S2. By allowing the X-ray beam to fall on the powder specimen C through the slit S1 and S2, now here the function of these two slits is to get a narrow pencil beam of the X-ray. The X-ray beam will be fall on the powder specimen C, which is stuck on the hair by means of the gum, and it is suspended vertically in the axis of the cylindrical camera called the Debye camera. So its position, it is suspended vertically in such a way that its position, it should be in the direction of the incident beam of the radiation. The photographic film is mounted around the inner surface of the camera, and it almostly surrounded around the specimen. So in order to receive the X-rays diffracted up to the 180 degree, means when the monochromatic beam of the fine beam of the X-ray, when incident on the powder specimen, then it will be get diffracted, so that the diffracted beam will be incident on the photographic film up to the 180 degree. That means here from this point to this point. So there is the formation of the concentric rings due to the diffractions here, and after the 180 degree there will be the formation of the formation of the cones or the rings due to the reflection of the incident beam from the powder specimen. When the diffracted or the reflected beam falling on the powder specimen, when the incident on the when the diffracted and the reflected beams falling on the photographic film, then it cut the film. Now here the width of the film is very narrow, and due to it only the part of the circular rings are registered on the film. So now in this case here we can see that only here we can see that only the part of the circular circular rings are recorded here, and the curvature of the rings reverse after the angle of the diffractions exceed the 180 degree. That means I have already told you that when the diffraction angle exceeds the 90 degree, that means from this point to this here, then there will be the reflection, and so we get again the concentric rings due to the reflections also. That is the back, you can see that the back reflection. If we consider the distance between the symmetrical lines on the stressed photographic films, say as the L1, L2 and the L3, if we consider the diameter of the cylindrical film is D, then the distance between these symmetrical lines can be determined by the L1 is equal to be the circumference multiplied by theta divided by the 360 degree. Now here d is the diameter of this circular ring. Therefore, the circumference is equal to the pi d, and now this total angle is equal to be the 4 theta. Therefore, we can write here the L1 is equal to be the pi d into the 4 theta divided by 360 degree. Therefore, we can express it in terms of that the theta. So for the first ring, the theta 1 is equal to be the 90 degree divided by the pi d into the L1. Similarly, for the second ring, theta 2 is equal to be the 90 degree divided by the pi d into the L2. So by using these values of the theta in the Bragg's diffraction condition, the interplanar spacing d can be determined. So students, you have to remember that by using the powder diffraction method, when the X-ray beam incident on the powder material, then it will be get diffracted, and the diffracted pattern generated on the photographic film in the form of the concentric rings. So by measuring the radius and in the form of the concentric rings here, but the width of the photographic film is very narrow, so we can observe the symmetrical lines on the photographic film, and if we measure the distance between these symmetrical lines, then from this we can find the value of the theta 1 and the theta 2. Then by substituting these values of the theta in the Bragg's diffraction condition, we can determine the interplanar spacing, that is d. Now here we are going to see the example of the X-ray powder diffraction produced during the X-ray scan. Now see here, this is the schematic representations of the X-ray powder diffractogram. Now here this is the X-ray tube. Now here this is the monochromator. Now this is the powder material. Now it consists of that the number of the tiny crystals, and when the beam will be get incident on this powder material, it will be get diffracted, and this diffracted beam will be get recorded by using the detector. Now here we can record the diffracted pattern on the photographic film also, or you can record the intensity of the diffracted beam by using the suitable detector. Now here the suitable detector is connected to the computer system, and as the sample and the detector are rotated, the intensity of the reflected X-ray will be recorded by the detector. And when the geometry of the incident X-ray incident on the sample, and when it satisfies the Bragg's equation, so the constructive interference occurs, and you will get the peak intensity. So that peak intensity can be recorded by with the help of the detector and the suitable computer system. A detector records and processes these X-ray signals and convert the signals to a count rate, which is then output to the devices as the printer of the computer monitor. So now in this way, when the beam of the X-ray incident on the any powder material, and when it satisfies the Bragg's diffraction condition, then it will be get diffracted, and it gives the constructive interference which having the maximum intensity, and by using the detector, we can record these signals and convert these signals to a count rate, and this can be, or this output can be observed or can be recorded on a printer or the computer monitor. Now see here, now this is the one of the type, this is the XRD. Now it is also known as the Xray Diffractogram. This is one of the Xray Diffractogram of the uneven material. After recording the intensity from the diffracted beam, then we observe the different peaks, and if we plot the graph of the intensity and the 2 theta, then we observe the different peaks here. Now here these peaks represent the lattice planes and therefore can be characterized by the Miller indices. So now in this case here, these different peaks are corresponding to the different orientation of the planes, and due to that they can be characterized by the Miller indices. By using this X-ray diffractogram, the set of the D spacing, that is the interplanar spacing between the atomic planes, can be easily calculated from the different values of the theta. So by plotting the graph of intensity recorded by the detector with the 2 theta, then we observe that there are the different peaks corresponding to the different orientation of the planes, and by using this we can determine, or we can obtain the D spacing, that is the interplanar spacing of the different crystalline planes here. Now then, what are the applications of the XRD? Now there are the number of the, nowadays the XRD having the very important role in the characterizations of the different materials in material science also and in chemistry also. Now I am going to share some applications of the XRD. The first one is, it is used to identify the crystalline phases and the orientations. We know that the different powder materials, or the different materials having the different phases, and the powder material consists of the huge number of the tiny crystals. They are oriented in a different direction. So with the help of the XRD, we can identify the crystalline phases also and their orientations also. Now we can determine the structural properties such as the lattice parameters. The lattice parameters in case of the unit cell, the A, B and C. Now A, B and C are the lattice parameters that can be detected by using the powder diffractions method. Similarly, the strain in that crystalline material, the grain size, the phase composition, preferred orientation and the thermal expansion. It is used to measure the thickness of the thin film and the multilayers also. Now it is used to determine the atomic arrangements. We know that in a crystalline material, we have seen in a first chapter the atomic arrangement in the crystalline structure. So that can also be determined with the help of the XRD. A crystalline substance can be distinguished from the amorphous. So if you want to distinguish the crystalline material from the amorphous, then the XRD is also useful. The X-ray powder diffraction is most widely used for the identification of the unknown crystalline materials, such as the minerals, inorganic, and the compounds. So now in this way you have to be remember about the basic principle of the powder diffractions method. Now the different parts of the powder diffraction method and the working of the powder diffractions method, and how to determine the despacing by using the photographic method also, and by using the suitable detector also. Now then, in the previous lecture we have seen about the two techniques of the X-ray diffraction. The one was the Lau method and second one was the rotating crystal method, and in this lecture we have seen the powder method. So now then, what are the basic difference between these? Basically the Lau method is used for the determination of the orientation of the crystalline planes and also for the determination of the symmetry of the crystalline planes. While the rotating crystal method is used for the determination of the lattice constant. But now in case of that the powder method, we can determine the lattice parameters. Now these are along the three edges of the any crystalline unit cell. The Lau method and the rotating crystal methods are useful only for the single crystal material, but the powder method is useful for the polycrystalline material. Now in case of that the Lau method, we need the we use directly the polychromatic X-ray radiations, but now in case of that the rotating crystal method and powder method, we need the monochromatic X-ray radiations. Now in case of that the Lau method, the sample is a stationary, so the glancing angle is fixed. But now in case of that the rotating crystal method, now the sample is rotated, so the glancing angle is also changing here. Now in case of that the powder method also, now the sample is rotating and or the detector is rotating, and due to that there is the variation in the glancing angle also. So remember about what is the basic difference between these three methods and what are the main applications of these three methods. So thank you.